diving into the history of comet exploration reveals captivating insights and unexpected turns of fate. In late 1993, the European Space Agency embarked on an ambitious project aiming to reach a comet and achieve the first-ever landing of a spacecraft on its surface. The vast expanse of the solar system is home to countless comets, and the scientists of the Rosetta mission faced the challenging task of selecting the most suitable object for their study. An ideal candidate was considered to be a comet orbiting within the ecliptic plane, which would simplify the rendezvous process. Additionally, it was crucial that the comet's closest approach to Earth coincided with the readiness of the spacecraft and its launch vehicle. Initially, the short-period comet Wirtanen was chosen, appearing to be the perfect fit for the mission. However, circumstances intervened. It became clear that the Ariane 5 rocket would not be ready for launch before 2004, meaning a missed opportunity window. Consequently, the agency's attention shifted to another short-period comet with the remarkable name Gerasimenko. The events that followed became a significant milestone in the history of solar system exploration, and for nearly 2 years, these two Ukrainian surnames were consistently featured in scientific publications and other media. This story begins in 1955 when a young Klim Churyumov from Mykolaiv enrolled in the Faculty of Physics at Kyiv State University, now known as Taras Shevchenko National University of Kyiv. After 2 years of studying theoretical physics, he was transferred to the Department of Optics, a move that didn't particularly excite the young man. Nevertheless, he continued to attend theoretical physics lectures, and eventually, he was transferred to the Department of Astronomy, where vacancies were available at the time. Despite astronomy not being his initial choice, this change of fate proved to be quite fortunate. As Klim Ivanovich himself recalled, astronomy turned out to be an extremely captivating field for him. While still a graduate student, the young scientist was offered the opportunity to study comets under the guidance of the distinguished researcher Sergei Sekspiatsky. Thus, Klim Ivanovich began his comet research at the Lesniki Observational Station of Kyiv University's Astronomical Observatory and also participated in various expeditions to observatories located in the southern regions of the Soviet Union, specifically in Azerbaijan, Armenia, Uzbekistan, Turkmenistan, and of course, Kazakhstan. In 1969, Klim Ivanovich led an expedition to the Astrophysical Institute's observatory near Almaty, Kazakhstan. He was accompanied by graduate student Svetlana Gerasimenko and Photolab assistant Lyudmila Chirkova, for whom this was their first such journey. Using a local telescope with a half-meter mirror, they began observing known comets and searching for new celestial bodies. The work involved capturing the same patch of sky twice, with an interval of 20 to 30 minutes. By comparing the two resulting images, they could detect comets that had slightly changed their position relative to the fixed stars. On September 9th, the group obtained their first photographic plates, capturing comet Sola. However, the weather then deteriorated, and observations resumed only 2 days later. On the night of September 11th to 12th, Svetlana Gerasimenko continued observations of several comets, including what was supposed to be Sola. After completing the observations, Svetlana and Lyudmila began developing the photographic plates, but the result was disappointing. One of the plates was partially overexposed. A frustrated Svetlana Gerasimenko initially wanted to discard the spoiled plate, but even defective plates could contain valuable information. In particular, a blurry image of comet Sola could still be discerned on this plate. In October, back in Kyiv, Klim and Svetlana began a meticulous analysis of all their observation results. And then it was time for the overexposed plate. The researchers measured the positions of all captured comets and found that the diffuse spot, which should have corresponded to comet Sola, was not in the correct place in the sky. It was shifted by almost 2 degrees from the expected position. But how could this happen if comets couldn't teleport? It had to be some other object. Klim and Svetlana carefully rechecked all the plates and eventually found comet Sola exactly where it was supposed to be. And on 4 other plates, they again saw the new object. After sending a telegram to the International Astronomical Union, they received confirmation that the object was indeed new, and this was its first observation. Thus, they discovered a new comet, which was subsequently named Churyumov-Gerasimenko in honor of its discoverers. Decades later, it was destined to become a superstar among comets, but that's another story entirely. Comet Churyumov-Gerasimenko is a typical representative of the numerous family of short-period comets, whose orbits, with a small inclination, allow them to complete an orbit around the Sun in less than 2 decades. These celestial wanderers, whose trajectories are under the constant influence of Jupiter's gravitational field, are known as Jupiter family comets. The widely accepted scientific hypothesis suggests that such icy bodies originated in the Kuiper Belt, a vast region of space populated by numerous objects orbiting the Sun beyond Neptune's orbit. Under the influence of gravitational perturbations and collisions, some of these bodies leave their established orbits and rush deep into the solar system, towards the rocky planets and the Sun itself. However, at the boundary of the inner and outer regions of the solar system, Jupiter acts as a kind of gravitational traffic cop, determining the further fate and direction of these uninvited guests from distant reaches. Engaging in gravitational interaction with this giant planet, comets gradually change their orbits until they are either permanently expelled beyond the solar system or fall into the Sun or one of the planets. Comet Churyumov-Gerasimenko is currently undergoing a period of orbital shift, steadily approaching the Sun. Analysis of its orbital evolution shows that until 1840, it made its closest approach to our star at a distance of 4 astronomical units, AU, which is 4 times the distance between Earth and the Sun. This distance was too great for stellar radiation to significantly heat the comet and form a characteristic tail, so it remained invisible to observers. However, in 1840, gravitational interaction with Jupiter caused the comet's perihelion, the point in its orbit closest to the Sun, to shift to 3 AU. Over the next century, the comet approached the Sun to $2.77, and in 1959, during another close encounter with Jupiter, its perihelion reached $1.29. Thus, with each orbit, the comet draws closer to the Sun. But before any concern arises, it's worth noting that Churyumov-Gerasimenko poses no potential threat to our planet. Computer models do not predict a collision in the foreseeable future. Moreover, there are no close approaches between Earth and the comet, with a minimum distance of 26 cents, ensuring a significant separation. Today, Churyumov-Gerasimenko completes a full orbit around the Sun in 6.45 Earth years. During this time, it has been observed 9 times during its closest approach to the Sun, with the next rendezvous expected in April 2028. This comet is medium-sized but still surpasses 99% of known asteroids, with an average diameter of about 4 kilometers. And indeed, it's a good thing that a close encounter with it is not a threat to us. However, the comet's true size and shape became known only thanks to the triumphant Rosetta mission. Before that, scientists only had a 3-dimensional model created based on observations by the Hubble Space Telescope, which did not entirely accurately convey the appearance of Churyumov-Gerasimenko. Generally, the idea of sending a mission to a comet arose after the resounding success of numerous space probes that investigated Halley's Comet in 1986. The European Space Agency played a key role in this historic event with its Giotto spacecraft. The scientific data it collected convincingly demonstrated that further close-up studies of comets were simply essential. One of the most cherished dreams of scientists was to obtain samples of cometary material and study them in Earth laboratories. It was with this goal that NASA and the European Space Agency began working together on the Rosetta mission. However, after evaluating the project's budget, NASA decided to withdraw its participation. ESA continued the work independently, abandoning the idea of returning samples to Earth and focusing on developing a spacecraft that would orbit the comet, as well as a separate module for landing on its surface. In 1993, the mission was finally approved, with its launch scheduled for 2003. The initial target was Comet Wirtanen, and en route, the spacecraft was planned to perform flybys of asteroids Steins and Odawara. However, problems with the Ariane 5 rocket forced a revision of the launch schedule and consequently, the main mission target, which ultimately became Comet Churyumov-Gerasimenko. For Klim Ivanovich Churyumov and Svetlana Ivanovna Gerasimenko, The news that the celestial body they discovered and named after them would be the target of a historic mission was a true triumph. This mission promised to unlock the mysteries of solar system evolution and even the origin of life on Earth. Klim Ivanovich was invited to the New Targets for Rosetta conference on the island of Capri. There, he presented a report on his comet and met with mission leaders, numerous scientists, and engineers who developed scientific instruments for the spacecraft and lander module. And on March 2, 2004, together with Svetlana Ivanovna, they were present at the Kourou spaceport in French Guiana and watched as Rosetta covered its first meters on the way to their comet, or, as Klim Ivanovich always emphasized, to the Ukrainian comet. The Rosetta mission, a true breakthrough in comet exploration, required an impressive 10 years of wandering through the solar system. After leaving Earth, the spacecraft performed a skillful maneuver, returning to its home planet a year later to gain the necessary speed for its further journey. Its path then led past Mars, where the red planet's gravitational field helped correct the trajectory and guide Rosetta back to Earth for another gravity assist maneuver. In February 2007, the spacecraft even dedicated time to scientific observations of Mars, collecting valuable data about the planet. Ultimately, Rosetta orbited Earth twice before receiving the final impulse needed to reach its main target. However, on its way to comet Churyumov-Gerasimenko, the spacecraft did more than just accelerate. Additional missions were carried out, expanding our knowledge of asteroids. Specifically, in 2008, Rosetta approached asteroid Steins, conducting observations from a distance of just 803 kilometers. And in July 2010, the spacecraft showed us asteroid Lutetia in all its glory, flying past it at a distance of just over 3,000 kilometers. Finally, in March 2014, Rosetta took the first image of comet Churyumov-Gerasimenko, which appeared as a tiny glowing dot against the distant globular cluster Messier 107. On July 14, 2014, the world held its breath upon seeing that the nucleus of comet Churyumov-Gerasimenko consisted of two massive parts connected by an isthmus. And on August 6, the spacecraft triumphantly met its target, flying over the comet's surface at a dizzying altitude of just 100 kilometers. Subsequently, Rosetta performed a series of complex orbital maneuvers, entering a stable orbit around the icy object at a distance of about 30 kilometers from the surface. Of course, the main feature of the comet that immediately caught the eye was its whimsical shape, resembling a rubber ducky, or, as Klim Ivanovich wittily compared it, traditional Ukrainian straw slippers. The origin of this unusual structure became the subject of heated debate immediately after the first images of the comet reached Earth. Scientists put forward two main hypotheses to explain such an unusual shape. The first suggested that the comet formed as a result of the fusion of two separate bodies. The second hypothesis claimed that it was initially a single large object that lost a significant portion of its material in the central region due to localized erosion. However, scientists soon found convincing evidence supporting the first hypothesis. Comet Churyumov-Gerasimenko indeed consists of two separate comets that once merged and now travel through space as a single entity. To reach this conclusion, a team of researchers from the University of Padua in Italy meticulously processed a series of high-resolution images of the comet's surface taken over nearly a year of the spacecraft's operation. By studying the surface in detail, they discovered over 100 flat, terrace-like areas. It turned out that these flat structures became more inclined as they approached the so-called neck of the comet. By performing 3D modeling, scientists determined the direction of inclination of all these terraces and visualized how they extended into the comet. It soon became obvious that all these elements were oriented around each of the two parts of the comet. The second important step was to establish the relationship between the orientation of the terraces and the comet's gravitational field. The logic is simple. Layers of cometary material should be oriented at right angles to the direction of gravity. Therefore, the team of scientists used computer models to calculate the force of gravity and its direction at the location of each layer. Two scenarios were considered. In the first, the comet was modeled as a single entity, and in the second, as a combination of two bodies, each with its own center of mass. The modeling results unequivocally showed that the orientation of the layers could only have formed in this way if both parts of the comet had previously existed as separate objects. The collision between them likely occurred at a very low speed, which allowed all the ordered layers of both comets to be preserved. Although erosion is not the primary cause of comet Churyumov-Gerasimenko's unusual shape, it certainly plays an important role in its evolution. Particularly interesting processes occur when the comet approaches perihelion, that is, the point in its orbit where it is closest to the Sun. At this time, intense sublimation of water ice begins, leading to ejections of gas and dust. In 2015, just 2 months before the comet reached perihelion, astronomers recorded striking changes in a region called Imhotep, located on the larger of the two parts of the comet. This region is characterized by relatively smooth areas covered with fine-grained material, as well as enormous boulders, the largest of which, named Cheops, reaches 45 meters in diameter. Since Rosetta's arrival, scientists had carefully observed this surface area for almost a year and noticed no changes. However, one morning in June 2015, they recorded the appearance of a new, almost circular structure. Subsequent images taken throughout June showed how this structure increased in size, and another joined it. By July 2nd, they had reached diameters of approximately 220 and 140 meters, respectively, and a new structure had begun to form. By the time the last image was obtained on July 11th, these three objects had merged into one large area, and two more new structures had appeared. The speed at which the surface changes occurred reached several tens of centimeters per hour, which is a rather rapid process. This is not surprising, as the Imhotep region is located near the comet's equator and receives an enormous amount of solar radiation. Among other notable changes recorded by the mission, the transformation of a cliff named Aswan stands out. Initially, Rosetta captured a large crack on it, which, however, disappeared by the time the comet approached perihelion in July 2015. As it turned out, a significant collapse occurred, exposing a bright, unaltered edge. Untouched water ice, hidden deep within the cliff, was observed at the site of the collapse. This area reflected solar radiation 6 times more intensely than the comet on average. Over time, however, the ice sublimated, and by August 2016, the cliff's brightness returned to its previous values. Additionally, scientists discovered an accumulation of debris at the base of the cliff and the appearance of new boulders. It is assumed that such collapses are caused by thermal stresses resulting from solar heating of the surface. First, cracks form, through which heat penetrates deeper. Then, gas released by heating expands these cracks, leading to collapse. However, changes on the comet are not solely due to solar radiation. One of the cracks on the comet's neck, discovered back in August 2014, has increased by approximately 30 meters. Additionally, a new crack 150 to 300 meters long was observed. According to scientists, this is related to mechanical stresses arising from the comet's rotation. Interestingly, near these cracks, a boulder about 4 meters wide shifted 15 meters from its original location. And another giant rock, 30 meters wide and weighing about 13,000 tons, moved a remarkable 140 meters. This is believed to have happened during perihelion, as several ejecta events were recorded near its previous position. There are 2 hypotheses explaining this movement: either the ground on which the boulder rested gradually slid, or one of the ejecta events propelled it such a significant distance. In any case, thanks to Rosetta, astronomers were able to see not only the changes occurring on the comet's surface but also to estimate the speed of these processes. However, the most exciting moment of the mission was the attempt to land the Philae module on the comet's surface. During the first 2 weeks in orbit, Rosetta collected detailed data on the surface characteristics, based on which the mission team identified 5 potential landing sites. Ultimately, in early November 2014, it was announced that an area called Agilkia would be the place where, for the first time in history, a spacecraft would touch a comet's surface. On November 12, Philae separated from Rosetta and began its descent to Churyumov-Gerasimenko at a speed of just over 3 kilometers per hour. At the European Space Operations Center in Darmstadt, Germany, specialists closely monitored the events. However, the landing did not go as planned. The harpoons, designed to anchor the spacecraft to the surface, failed to deploy. Due to the low gravity, Philae bounced off the surface and flew about 1 kilometer for 2 hours before touching down again. This time the bounce was less significant, and 7 minutes later, Philae became the first spacecraft in history to successfully land on a comet's surface. The lander's exact location remained unknown. It was presumed to be in a shaded depression and possibly not upright. Nevertheless, Philae was stable and began transmitting data from the surface. All 10 of its scientific instruments were functioning. Unfortunately, due to limited battery power, Philae operated for only a short time and ceased transmitting signals after 3 days. The lander briefly woke up in June 2015 but then fell silent permanently. Despite its brief operation, Philae made significant contributions to science. During its descent and landing, it measured the comet's magnetic field and detected its absence, as well as the absence of magnetized rocks that could have survived since the formation of the system. This indicates that magnetic fields did not play an important role in the process of small particles aggregating into larger bodies such as asteroids, comets, and planets. The most important discoveries were made during the first contact with the surface. Material samples entered the probe's instruments, and Philae determined their chemical composition, finding 16 organic compounds rich in carbon and nitrogen. 4 of these had not been previously observed on comets. Additionally, the lander analyzed the composition of the comet's gaseous envelope, detecting a high concentration of water vapor, carbon monoxide, and carbon dioxide, as well as small amounts of organic compounds, including formaldehyde. It is important to note that some of these compounds play a key role in the synthesis of amino acids, sugars, and nucleic acids, the fundamental components of life. For example, formaldehyde is involved in the creation of ribose, a component of DNA. And all this, on the surface of a body that Klim Churyumov called a time capsule, containing pristine material preserved since the birth of the solar system. Meanwhile, Rosetta continued its work in orbit. One of the first important discoveries was the finding of differences between the water on comet Churyumov-Gerasimenko and the water on Earth. The ratio of deuterium atoms to hydrogen in the cometary water was 3 times higher than in Earth's water. This means that the water we drink and are largely composed of is unlikely to have a cometary origin. As part of the mission, an experiment was conducted to determine the comet's internal structure using radar. Rosetta measured the propagation of radio waves between the orbiter and the Philae lander, passing through the comet's nucleus. This allowed scientists to establish that Churyumov-Gerasimenko has a very porous structure, with porosity levels of 75 to 85%. Essentially, comets are aggregations of rubble held together by gravitational forces, with extensive voids within their interiors. This fact is confirmed by analyzing the comet's gravitational effect on the spacecraft. The high porosity indicates that the comet's formation was a delicate process, during which many small cometesimals stuck together at speeds not exceeding 1 meter per second. In other words, they touched rather than collided, which precluded melting and the formation of a dense structure. During its time orbiting the comet, Rosetta discovered a number of new substances not previously seen on comets. The biggest surprise for scientists was the detection of molecular oxygen in significant quantities, which contradicts current models of solar system formation. According to these models, oxygen molecules should have disappeared before the comet formed, more than 4.5 billion years ago. It was expected that during the tumultuous processes of sun and planet formation, oxygen would react with hydrogen to form water. This fact remains the main mystery associated with comet Churyumov-Gerasimenko, and has no convincing explanation. For over 2 years, Rosetta orbited the comet, accompanying it on its journey through the solar system. In September 2016, comet Churyumov-Gerasimenko had moved significantly away from the Sun, approaching Jupiter's orbit. With decreasing solar radiation, the spacecraft received less and less power. Moreover, more than 12 years in space is a serious duration, especially for the operability of scientific equipment. The option of putting Rosetta into hibernation during its aphelion was considered, but there was a risk of the heating system failing and the spacecraft being unable to reawaken. The mission's scientific team decided not to take the risk and to maximize the opportunity for data collection. It was proposed to direct the spacecraft to collide with the comet to obtain high-resolution images during its descent. Shortly before the impact, Rosetta located the Philae lander on the comet's surface, which, as presumed, was in a shaded crevice and could not receive solar energy. The discovery of the lander, which had been sought for almost 2 years, was an important and emotional moment for the mission team. At the end of September, Rosetta reunited with its little brother, colliding with the comet at a speed of just 3 kilometers per hour. The spacecraft was directed to the Maat region, known for its pits from which dust and gas are ejected into space. Thus, on September 30, 2016, the mission was concluded. 2 weeks later, on the night of October 14 to 15, Klim Ivanovich Churyumov passed away. According to Klim Ivanovich's student, Vasily Ponomarenko, an astronomer and PhD in physics and mathematics, there might be a connection between the completion of the mission and Klim Ivanovich's passing. Ponomarenko stated, Klim Ivanovich was deeply concerned about the mission's progress, starting from Rosetta's awakening in 2014 after several years of hibernation. There was a risk of losing contact with the spacecraft. Klim Ivanovich experienced this phase very profoundly and emotionally. On the other hand, Klim Ivanovich had 3 waves of fame. The last one, related to Rosetta in 2014 to 2015, made him sought after worldwide. He was invited to conferences, with travel and accommodation paid for, and being a person dedicated to popularizing science, he never refused. Perhaps he felt this was his last wave of fame and worked tirelessly. Such physical and emotional strain likely took a toll on his health. After the discovery of the comet, Svetlana Gerasimenko moved to Tajikistan in the 1970s, where she continues to work at the local astrophysical center. Klim Ivanovich continued his comet studies as a researcher at the Astronomical Observatory of Kiev National University. In 1986, in collaboration with astronomer Valentin Solodovnikov, he discovered a second comet named after him, Churyumov-Solodovnikov. In the 1980s, at his initiative, minor planets discovered by Ukrainian astronomers were named Kobzar, Kamenyar, and Znany, as well as after prominent Ukrainian figures, Taras Shevchenko, Ivan Franko, and Hryhorij Skovoroda. Throughout his distinguished scientific career, Mr. Churyumov served as a professor at Kiev National University, was elected a corresponding member of the National Academy of Sciences of Ukraine, and headed the Kiev Planetarium Educational Center. He authored hundreds of scientific papers, including 5 monographs and 5 textbooks. Furthermore, Klim Ivanovich actively participated in science popularization, finding inspiration even in poetry. He showed deep respect for both established scientists and enthusiastic amateur astronomers, presenting scientific reports on complex topics and conducting popular lectures for a wide audience with equal enthusiasm. Klim Ivanovich, possessing extensive knowledge of history, sincerely identified as Ukrainian and was a devoted patriot of his country, believing in the imminent collapse of the Russian Federation. He found solace in poetry, writing poems for children and even composing an anthem for the Maidan. In 2013, returning from work, he repeatedly took a considerable detour with Klim Ivanovich through Maidan, as the unfolding events deeply affected him. His poem, which he called the Maidan Anthem, contemporaries believed perfectly captured the prevailing atmosphere. Although the author had good teachers, it was working under Klim Ivanovich's guidance that made him realize he had met a truly great teacher. In 2014, like many scientists, Klim Ivanovich was struck by the shape of the comet he discovered, comparing its surface to mountain ranges and suggesting they be named after the Ukrainian Carpathians or Hoverla. He wanted to name one of the objects on the comet's surface after his hometown, Mykolaiv. However, the astronomical community opted to use the names of Egyptian gods for the objects. Klim Ivanovich always emphasized his affiliation with Ukrainian science and expressed dissatisfaction when the press referred to him as a Soviet or Russian scientist. He firmly considered his comet a Ukrainian discovery and referred to it as exclusively Ukrainian. Although the scientific data obtained from the comet will be analyzed for many years to come, Klim Ivanovich had the unique opportunity to witness his discovery in all its glory. Moreover, he was even fortunate enough to hear it. Magnetic oscillations resulting from the interaction of solar wind with the comet's surrounding matter were converted into sound waves by the mission team, and a German composer adapted these sounds for human perception. Thus, the world not only saw the comet up close but also heard its singing.